Hello, greetings from Portugal. My name is João Sobrinho and today I will report on new fundamental results concerning optimal path routing. This is joint work with my student Miguel Ferreira. We offer two main contributions: a solution to the problem of optimal path routing for an arbitrary optimality criterion and a solution to the problem of optimal path routing concurrently for multiple optimality criteria. An optimality criterion is a relative valuation of the performance metrics that characterize paths in a network. Standard routing protocols such as BGP, EIGRP, DSDV, and Babel route on optimal paths only for a very restricted class of performance metrics. And moreover, they are unable to route concurrently on different valuations of those performance metrics. Optimal paths come in different forms. An optimal path to convey a file across a network is a path that minimizes a linear combination of delay and inverse bandwidth. An optimal path to stream a video across a network is a path that minimizes delay as long as its bandwidth is sufficiently high. If it is not sufficiently high, then it is a path of maximum bandwidth. And in wireless networks, we find many different notions of optimal paths supported on elementary metrics such as, in addition to delay and bandwidth, loss probability, co-channel interference, and, in the case of battery-powered devices, energy consumption. A routing algebra provides a unified treatment of optimal paths, abstracting away the specificity of performance metrics. It consists of a set of attributes, a total order on attributes, and an extension operation on attributes. Attributes represent arbitrary performance metrics. The total order on attributes defines an optimality criterion. The optimal attribute of a set is the most preferred attribute of the set. And the optimal attribute from a source to a destination in a network is the optimal attribute among all path attributes from source to destination. The extension operation allows calculation of the attribute of a path from the attributes of its constituent links. The prototypical routing algebra is the one underlying shortest paths. In this case, attributes are non-negative real numbers. The total order is the less than or equal order, and the extension operation is addition. A vectoring protocol generalizes a distance vector protocol to an arbitrary routing algebra. It instantiates a separate computation per destination, whereby nodes continually extend, elect, and advertise attributes to reach the destination. Whenever a node receives an advertisement from an out neighbor, it extends the attribute of the link to the out neighbor to the attribute advertised by the out neighbor, thereby obtaining a candidate attribute to reach the destination via that out neighbor. Then it elects the optimal attribute among its candidates and advertises it to its in-neighbors. Vectoring protocols are tied to a destination-based forwarding of data packets. A distance vector protocol does route data packets along shortest paths, but does a vectoring protocol route data packets along optimal paths? Not always. A simple example illustrates the non-optimality of vectoring protocols. Attributes are pairs with length. The shortest widest order is such that width length WL is preferred to width length W prime L prime if its width is greater or the widths are equal and its length is smaller. Thus, width takes precedence over length in establishing preferences among width lengths. Widths extend with minimum and lengths extend with addition. So we have here a small network, and the shortest widest path from node V to node X is path VWX with length 20,5, which is the extension of 20,4 of link VW with 20,1 of link WX. And the shortest widest path from node U to node X is path UVX with length 10,5, which is the extension of 10,3 with 10,2. Destination X initiates the vectoring protocol computation by advertising infinity 0 to node W. Thus, W learns 20,1 from X. Node V learns 20,2 from X, and it learns 10,2 2, from X, and it learns 20, 5 from W. On account of its greater width, 20, 5 is selected at V and advertised to node U. Node U learns 20, 8 from V, which is the extension of 10, 3 with 20, 5, and it learns 5, 2 from W. Node U forwards data packets to V, which forwards them to W, which forwards them to X, and data packets travel along path UVWX, which is not the shortest widest path from U to X. The key property that guarantees optimality of vectoring protocols is isotonicity. The extension operation is isotone for the total order if, when B equals or is preferred to C, implies that A plus B equals or is preferred to A plus C. In other words, the relative preference among attributes is preserved by extension, with the implication that locally optimal routing decisions are globally optimal as well. If isotonicity holds, then a vectoring protocol routes on optimal paths. If isotonicity does not hold, then a vectoring protocol does not route on optimal paths in general. The problem is that most concrete optimal paths found in practice do not satisfy isotonicity. None of the examples I gave before satisfy isotonicity in general. What do we do? An idea is to reduce the total order such that the extension operation is isotone for the reduced order. Reducing an order means declaring some pairs of attributes incomparable, neither of the two attributes of a pair being preferred to the other. An isotonic reduction of a total order is a partial order that is contained in the total order and satisfies isotonicity. So we are led to partial orders. An isotonic reduction trades totality of the order for isotonicity. What now? First, we need to formulate a path problem in terms of partial orders and relate that problem to optimal attributes. Given a partial order, a dominant attribute of a set is an attribute such that no other attribute of the set is preferred to it. And the dominant attribute from a source to a destination in a network is a dominant attribute of the set of all path attributes from source to destination. So the set of dominant attributes from source to destination is a set of pairwise incomparable attributes. The important observation is made that if the partial order is the reduction of some original total order, then the original optimal attribute is found within the dominant attributes. The second idea is to design a partial order vectoring protocol that operates with sets of attributes rather than with single attributes. Nodes extend, elect, and advertise sets of attributes rather than single attributes. Whenever a node receives a set of attributes from the neighbor, it extends the attribute of the link to the neighbor with each of the attributes advertised by the neighbor, thereby obtaining a set of candidate attributes. Then it performs the election of the dominant attributes among its candidates. And if the election shows some change, the elected attributes are advertised to neighbors. Now, since a node elects more than one attribute per destination, destination-based forwarding does not work. Rather, every node locally assigns a unique label to each of its elected attributes that is advertised alongside the attribute to e-neighbors. Data packets are guided along paths through label switching at intermediate nodes. If isotonicity holds, then the protocol routes on dominant paths. Let me give you an example of these ideas. The product order on width lengths is such that width length WL is preferred to width length W', if both its width is greater than or equal and its length is smaller than or equal than those of W'. The product order on width lengths is a partial order, given two width lengths such that one has greater width but the other has less length. These two width lengths are incomparable. And the product order on width lengths is a reduction of the shortest widest order. A width length that is preferred to another in the product order is also preferred to that other in the shortest widest order. In this network, which is the same as before, there are two dominant width length paths from V to X. Path Vx with width length 10, 2, and path VWX with width length 20, 5. 20, 5 and 10, 2 are incomparable. One has greater width, the other has smaller length. The two dominant width length paths from U to X are paths UVX width length 10, 5 and path UWX width length 5, 2. Note, and this is very important, that the shortest widest paths are found among the dominant width length paths. Destination X initiates the vectoring protocol computation, advertising infinity 0 to W. W elects 20, 1 from X. Then node V learned 10, 2 from W and 20, 5 from X, as before. But now, according to the product order, these two width lengths are incomparable. Both are elected. Node V distinguishes them by assigning label 2 to 10, 2 and label 4 to 20, 5. Both these width lengths and the associated labels are advertised to node U. Thus, node U learns 10, 8 and 10, 5 from V, and it learns 5, 2 from W. 10, 5 and 5, 2 are incomparable, and 10, 8 is less preferred than 10, 5. So the elected attributes at U are 5, 2 and 10, 5. If node U now wants to send data packets to X along the shortest widest path, all it has to do is locally identify 10, 5 as the shortest widest width length from U to X and read from the corresponding entry. It sends data packets to V with label 2. V switches the label from 2 to 1 and delivers the data packets to node X. So far, I've talked about routing on a single optimality criterion, but the title of the talk promises routing on multiple optimality criteria, and that problem has the following formulation. Again, there is a set of attributes, there is an extension operation from which the attribute of a path is obtained from the attributes of its links, and then there is a collection O of optimality criteria, each of which is represented by a total order on attributes. And the goal is for every flow of data packets to be routed on the optimality criterion that is most appropriate for that flow. How do we do that? Well, the idea is simple. We perform the intersection of all the total orders, and the intersection of all total orders gives a partial order. And now we know how to route according to a partial order. Let me exemplify with the same network as before. The widest shortest order is such that width length WL is preferred to width length W prime L prime if its length is smaller or the lengths are equal and its width is greater. So it's the opposite. The widest shortest order is the opposite of the shortest widest order in terms of the precedence between width and length in regard to the preferences among pairs with length. The widest shortest path from A to B is a path of maximum bandwidth, maximum width among those of minimum length from A to B. The intersection of the widest shortest order and the shortest widest order is the product order. So we are back to this network, and we now see that node U can send data packets to X along the widest shortest path. All it has to do is to identify 5, 2 as the widest shortest width length to reach X. Reading from that entry, it sends data packets to node W with label 2. Node W replaces label 2 with label 1 and delivers them to node X. So with a partial order vectoring protocol, it is possible to route different flows along different paths corresponding to different optimality criteria. This slide summarizes the workflow for routing on multiple optimality criteria. We start with a collection of optimality criteria. perform the intersection of the corresponding total orders, take the isotonic reduction, and we arrive at a partial order. Then we can use a partial order vectoring protocol to enable routing on dominant paths. The optimal paths of each criteria are selected by the sources among the dominant paths, and data packets are guided along these optimal paths through label switching at the intermediate nodes. I'd like to make 3 comments. The greater the partial order, the more the pairs of attributes that are comparable, the less the number of dominant attributes from source to destination in a network, and the more efficient the routing protocols. In short, we aspire to isotonic reductions which are as large as possible. It can be shown that every total order has a largest isotonic reduction. Second comment, other routing problems lead naturally to partial orders. The paper gives an example from service chaining. And third comment, there are other protocols that can work with partial orders. And again, the paper gives an example of a lightweight protocol that's more amenable for programmable hardware. What is the practicality of our approach to routing on multiple optimality criteria? So we developed a computational toolbox to answer 2 main questions. What are the sizes of sets of dominant attributes? And what is the speed of convergence of partial order vectoring protocols? We based our evaluation on 6 rocket fuel topologies, characterized by their number of nodes and links, as shown in this chart. Each link in every topology is annotated with a width and a length, so we consider the product order on width lengths. The number of dominant width lengths from source to destination is always upper bounded by the number of distinct widths in the network. And the number of distinct widths in the network is shown here on the 4th column. The 5th column shows the computed average number of dominant width lengths from source to destination in each of the networks. That number ranges from 1.9 to 3.7. And the main conclusion is that this number is rather small. It is much less than its worst case, which is the number of distinct widths in the network. The plot on the right-hand side of the slide shows the complementary cumulative distribution function of termination time for when a new destination is announced in the network over all possible destinations. We run vectoring protocols for 3 orders: the widest shortest order in yellow, the shortest widest order in blue, and the product order in green. There are 2 main conclusions to be drawn from this plot. The CCDF of the termination times for the widest shortest order and the product order have similar behaviors. The average termination time for the product order is 50% higher, but the product order elects 2.5 dominant attributes per node per destination, whereas the widest shortest order elects just 1. Both orders satisfy isotonicity. The relatively good performance of the product order on width lengths is because the multiple dominant attributes from source to destination are elected in parallel during execution of the protocol. The second conclusion is that the average termination time for the shortest widest order is worse than the termination time for the product order on width lengths. And this is because of isotonicity. The product order on width lengths satisfies isotonicity, and the shortest widest order does not satisfy isotonicity. Isotonicity not only guarantees optimality of the solutions, but it also promotes fast convergence. The plot on the right shows the CCDF of the termination time for a link failure over all link failures. Briefly, we just make 2 comments. First, some link failures have only a local impact on the state of the protocol, and the shortest widest order, again, is the one with the heaviest tail of termination times. We approach the end of the talk, and I would like to summarize the main ideas. We stated 2 routing problems and offered solutions to those problems. optimal path routing for an arbitrary optimality criterion, and optimal path routing for multiple optimality criterion. In the process of developing solutions to these problems, we introduced two new concepts to routing: the concept of largest isotonic reduction of a partial order and the concept of intersection of total orders or partial orders. Both concepts lead to partial orders, and we designed vectoring protocols that compute on partial orders. More research is needed in this space. We suspect that there are other routing problems that can be formulated in terms of partial orders. A survey is needed. Our evaluation was preliminary. We would like to have access to realistic topologies and metrics to be able to perform a more comprehensive evaluation of routing on multiple optimality criteria. And last, we look forward to implementations of lightweight partial order vectoring protocols in programmable hardware. Thank you for listening, and please get in touch. We welcome your feedback.